Are you tired of flipping through every single page of dictionary and trying to find a one specific word? Well, have no fear friends, let's do it with the power of elimination. Assume you won't look up the word internet in a dictionary. You grab your dictionary, give it a good shake and land on a random page that starts with the letter M. You know that your word must be located before that page, so you can eliminate the right half of the pages. In the next round, you land up on the page that's starting with the letter F, and you know that letter I comes after it. So that means you can eliminate the left half of the pages. Eventually you might land on the page that starts with the letter I, and voila, you found your word in there. By using this simple technique of comparing the alphabetical order, you can quickly and efficiently narrow down your search to a specific section of the dictionary. In computer science, we call this as binary search. But why is it so important? In computer science, every time you flip a page is considered as an operation. The fewer the operation you have, the more efficient your algorithm is. Imagine you are searching for a word in dictionary by flipping through every single page. The worst case scenario, you will end up on the last page where the words begin with Z. In sequential search algorithm, the worst case complexity would be the number of pages in a dictionary. This is referred to as linear time complexity. You can see in this graph when the search operation goes on, your search space also reduces linearly. If you apply sequential search on a search space of different sizes, you will observe that as the number of elements in the search space increases, the number of worst case operations also increase linearly. So what about binary search worst case scenario? Each time you search, you eliminate half of the searching space. This means that number of remaining search space is reduced by half after each operations. Now, if you draw a graph with the number of elements and its worst case operation count, you can see a logarithmic graph. We can call binary search as logarithmic complexity. Let's analyze what happened when we apply binary search to every single word in dictionary. Let's make things easier. We will assume each letter has a single page in the dictionary so that our whole dictionary having only 26 pages. We're going to start with the middle character M. If they match, we are done. If not, we must choose either the left or right half of the alphabet. Once we select which half we want, then we can eliminate the other half, and again we can select the middle character. We can repeat this process, narrowing down our search until we ended up with the letter we are looking for. Looks familiar? Yeah, that's right. It's a binary tree. There is much more general way of representing a binary tree, also known as btree. Instead of having only one single element per node and two branches per node, we are leveling up to a btree where we can have multiple elements per node and multiple branches per node. Now let's take a look at what happened when we construct our dictionary as a btree. The root node contains multiple characters, each with a reference to the left and right, pointing to the value that are lower or higher in the relation to its own value. So this holds true for child node as well. btree has many applications including efficient memory management, data compression techniques, powering search engine and information retrieval systems. But let's have a closer look at database and how they use btree for indexing. Imagine having a table full of data and need to access it in the quickest and most efficient way possible. The first step is to generate a unique indexing key for each of these rows. Each row can be uniquely identified with an index. The index is also known as the key, and the rows are also known as the payload. Now, we have a set of keys and payloads that we need to keep in the database. First, the database sequentially store these payload within its file system, but remember that actual implementation is a little more complicated with the techniques such as paging. For the sake of simplicity, we will not discuss them in here. Now it take the key and generate btree based on the value of these keys. Each of these keys has a reference to the payload that it holds. This is now referred to as the clustered index. A clustered index is a tree representation of the unique key, and it can be used to find the payload by searching on it with the unique key. Now, if we know the indexing key, you can easily search for any entry on this btree. But what about the other columns such as name, marks, and age? For each of these, we can create a new btree. Each of the node elements in those btree has reference to an indexing key. Now, if you need to search a name, you can search the name index and find the unique indexing key. Once you locate the unique indexing key, you can perform another search on the clustered indexing tree to locate the corresponding payload. The actual implementation and how the database store these data are a little bit more complicated. However, using btree indexing, this is how database efficiently store their data. If you have any question or comment about btree indexing or anything else related to the databases, please leave a comment in the comment section below. And don't forget to subscribe to our channel for more informative videos like this. Thank you so much for watching, and we will see you in the next one.